A capacitor is an electrical device consisting of two parallel consecutive plates separated by an insulating material called the dielectric material. Connecting leads are attached to the parallel plates. In a capacitor, the electric charge is stored in the form of an electrostatic field between the two conductors or plates due to the ability of dielectric material to distort and store energy while it is charged and keep that charge for a long period or till it is discharged through a resistor or wire. In the neutral state, both plates of a capacitor have an equal number of free electrons. When the capacitor is connected to a voltage source through a resistor, the negatively charged electrons are removed from plate A and equal numbers are deposited on plate B. Plate A becomes positive with respect to plate B. The current enters and leaves the capacitor, but the insulation between capacitor plates prevents the current from flowing through the capacitor. The ability to store energy in the form of electric charge is called capacitance. A farad is the unit of capacitance, and a coulomb is a unit of charge, and volt is a unit of voltage. Capacitance is mathematically expressed C equal to Q over V. The capacitance of a capacitor is determined by four factors: area of the plates, distance between the plates, type of dielectric material, temperature. The dielectric area is increased, the amount of energy stored in the dielectric material is increased, and the capacitance also increased. The strength of electric field between plates decreases when the distance between plates increases. The ability of a dielectric material to distort and store energy is indicated by its dielectric constant, represented by letter K. In ceramic capacitors, the discs are made by using ceramic as an insulator with a silver deposit on each side of the plates. Mica capacitors consist of alternate layers of metal foil and thin sheets of mica. The metal foil forms the plate, with alternate foil sheets connected together to increase the plate area, thus increasing the capacitance. Electrolytic capacitors are polarized so that one plate is positive and other negative. These capacitors are used for high capacitance values over 20,000 microfarad. Electrolytic capacitors are available in two types, aluminum and tantalum. One particular point you must always remember about the electrolytic capacitors is that one end is positive and the other end negative. Since electrolytic capacitor is polarized, the positive plate must always be connected to the positive side of a circuit. Be very careful to make the correct connection and to install the capacitor only in a DC, not in AC. Special electrolytic capacitors are manufactured for use in AC circuits. These are listed as non-polarized. An AC electrolytic capacitor is really two electrolytic capacitors packaged in a single container. There are several types of plastic film capacitors and older paper dielectric capacitors. Variable capacitors are used in a circuit when there is a need to adjust the capacitance value either manually or automatically. A capacitor is constructed with several plates that mesh together. One set of plates can be moved relative to other, thus changing the effective plate area and the capacitance. The movable plates are linked together mechanically so that they move when a shaft is rotated. Trimmers and padders are adjustable capacitors. They have screwdriver adjustments and are used for very fine adjustment in a circuit. This is an electrolytic capacitor. To check it, we select a range of 200 ohms in multimeter. We have to check twice by changing the multimeter probes. We get some reading in the multimeter and it disappears. Again, changing the probes in the capacitor terminal, we get some reading and it disappears. This capacitor is good. We are checking another capacitor. The multimeter shows close to 0. The capacitor is short. Here we are going to see the procedure for testing the capacitor for charge and discharge. Initially, touch both leads of the capacitor with a voltmeter. If there is any deflection, contact both leads through a resistance for sufficiently long time. Do not touch the capacitor leads by hand. High voltage retained by a charged capacitor will give a shock. Form the 12-volt circuit for testing the capacitor. Keep the switches open.
Two switches S1 and S2 are in closed positions. S1 is connected to a 12-volt battery. S2 is connected in series with the ammeter. There are 4 resistors of different values connected in series with a 12-volt capacitor. Now, we are going to close the supply S1 and S2. Now, we will observe the deflection in ammeter and voltmeter.
Record the deflection of the ammeter at the instant the switch is closed to position 1. Observe the voltmeter reading at equal intervals of time, at least 4 readings from 0 to the maximum deflections to be taken. Record the time and voltage. Repeat the steps by changing the value of the series resistance. Open the switch and observe the voltmeter reading for 5 minutes. Close the switch to position 2 and observe the voltmeter and ammeter readings. Repeat the test for different values of capacitance rated for different voltages. The testing voltage should be nearest to the voltage rating of the capacitor. Keep the ohmmeter selector switch at the higher range. Step 1. Discharge the given capacitor. Step 2. Connect the ohmmeter to test the capacitor and observe the meter deflection. While testing the polarized capacitor, the positive terminal of the capacitor is to be connected to the positive terminal of the ohmmeter and negative terminal to the negative terminal of the ohmmeter. If the ohmmeter indicates some resistance, there is some leakage, no deflection. Open. Deflects and return back slowly. Capacitor in good condition. Continuously shows 0 reading. Short.